Okay, in this video lesson, we're going to talk about different quantities that we use to measure gases, and then we'll also look at how to convert between those different quantities, those different units for each of those quantities. Okay, so by the end of it, we should be able to use appropriate terminology related to gases, pressure, temperature, volume, and standard conditions, and then also convert between different units for a given quantity. Okay, so a couple of things that we use to measure gases that we don't use to measure other substances like liquids and solids are pressure, for instance. Okay, this is a unit that we use almost exclusively for gases. I guess we could use it for fluids. So sometimes with liquids as well, okay? But specifically for gases, because pressure is going to kind of determine the number of collisions that are occurring and the force of those collisions with between the particles of the gas and the interior of the container that the gas is found in. So it's a measure of the force exerted by a gas over the entire surface area of the container. Okay, that is, the more collisions and the stronger the collisions with the wall of the container, the higher the pressure will be. Okay, so a reminder here, pressure is defined as the force over an area. So we can kind of see that in the definition there. Okay. We use different units, okay, to measure pressure. If we were measuring the gauge pressure of the air in our tires, we'd probably use PSI, or pounds per square inch. Okay, pounds actually is an imperial unit for force rather than mass. And then also per square inch, we're dividing by the area in inches. Okay, but some more classical units, and they were developed to actually measure the pressure of air and air pressure. Okay, one of the first ones is the millimeters of mercury. So millimeters of mercury are come about. The reason why we use that is that if we were to look at a barometer, okay, there'd be a tube that has one end is closed, the other end is open, okay, and the tube would actually have a little curl in it so that you could have a little pool of mercury open to the atmosphere, and the atmospheric pressure, the pressure that the gas actually exerts on us and on that pool of mercury is enough to actually, under normal conditions, push that column of mercury up almost a meter, so 760 millimeters. Okay, and that's where this unit comes from. Okay, so millimeters of mercury. Identical to it is torr. This was because Torricelli was involved in designing this instrument to measure pressure, or atmospheric pressure. So these two are identical. But if we wanted to get more into our metric system, we would want to use metric units of force and area. So for force, it's newtons. For area, it's meters squared. So defined as 1 Pascal, okay, is 1 Newton per meter squared. So the unit of force over the unit of area, okay. Atmospheric pressure exerts a much higher pressure than just 1 Pascal. It's more in the kilopascals range. Okay, so 1,000 pascals is 1 kilopascal. So we can use those prefixes that we have for metric system. And you'll see in a second, atmospheric pressure is about 100 kilopascals. So it makes sense that we might even use another unit that is based on the metric system, where we're using small numbers. So 1 bar is defined as 100 kilopascals. So it's still fairly metric, but there's no prefixes. And it is really defined in order to relate it really closely to atmospheric pressure. A final unit that's used is atmospheres, and atmospheres is defined according to all of these other units that I have listed here. So 1 atmosphere is 101.325 kilopascals. It's also, if we kind of bring in the bar, because 1 bar is 100 kilopascals, 1 atmosphere would be 1.01325 bars. So these are fairly close, and that's probably the reason why the bar was developed. Remember, normal atmospheric pressure would be 760 millimeters of mercury, or torr. It does fluctuate depending on the weather and elevation. So this is mainly defined as the pressure found at sea level. And then in PSI, it'd be 14.7 PSI, pounds per square inch. Okay, so that's one quantity that we will measure. So figuring out, it is kind of like a concentration in many ways. The higher the pressure, the more concentrated the particles are in the gas. And so they're going to make more collisions with the walls of the container, and they're going to be stronger. But other measurements that we might want to use for gases are also knowing what the volume is. Okay, so we're fairly familiar with volume after doing the mixtures unit and the solutions unit. Okay, we've got liters, we've got milliliters. Those are the main units for capacity or volume with fluids and solutions. Okay, we can also measure it in cubic meters, okay, or even cubic centimeters. The nice thing about cubic centimeters is they are directly related to the milliliter. So 1 milliliter is equal to 1 cubic centimeter, or cc, and it's often used in syringes. So I got a few little conversions here to show you. The one that makes most sense is the 1,000 milliliters is 1 liter. Also mention this here as well. 1 milliliter is 1 centimeter cubed, or 1 cc. Now this one's a little bit stranger. Okay, 1 meter cubed is equal to 1,000,000 cubic centimeters. Okay. Now, where does that come about? Well, if we wanted to actually create something that has a volume of 1 meter cubed, we would need a box that has a width of 1 meter, a length of 1 meter, and a height of 1 meter. If we converted each one of these meters into centimeters, they would be 100 centimeters each one. When we multiply those hundreds by each other, that's where we get 100 cubed, or 1,000,000. Okay, so we got to be careful when we're converting between linear measurements like we might have with meters and centimeters, and cubic or even squared units. Okay, they're not exactly the unit difference if you just you go for linear measurements. Okay, so meter to a centimeter is always 100 centimeters, but when we square it, now we have to square that conversion, so we got to keep an eye on that. That's shown here as well. Okay, so what that means is 1 cubic meter will now be 1,000,000 milliliters, or if you divide by 1,000, you get 1,000 liters. Okay, so quite a bit of volume there. The last thing that we might be interested in measuring about gases is the temperature. Okay, temperature is the measure of the average speed or the average kinetic energy of the particles in a sample. Okay, very simply, colder temperatures, the particles are moving slower on average. Higher temperatures, the particles are moving faster. So it kind of makes sense that we might want to be able to link these different units together. Obviously, if you think about it, if the temperature goes up, all of a sudden the particles are moving more rapidly and probably with more energy. They're probably going to exert a higher pressure if they're a gas in a container. Okay, and we've probably had experiences like that where things get too hot and they could explode. In terms of temperature, there's two main systems that we use. Again, imperial and metric. Fahrenheit, okay, often used for certain things, but Celsius for the metric system. So we want to get used to using that. Some kind of little, just to have a sense of what Fahrenheit does do. Having some benchmarks is important. 32 degrees Fahrenheit is melting point of ice, whereas 0 degrees Celsius is the melting point in Celsius. 210 Fahrenheit for boiling point of water, 100 degrees in metric. This is the neat thing about those two systems, is that they intersect each other at -40. So they're the same value in both scales at -40. So -40 Fahrenheit is the same as -40 Celsius. Now, when we're doing calculations with some of the laws there shortly, we do not want to use either of those systems. We want to use Kelvin or absolute temperature. Essentially, we want to get rid of all the negative temperatures there and start from 0, basically. Kind of like how volume does. There's no such thing as a negative volume, and pressure does as well. There's no such thing as a negative pressure. There might be a difference in pressure, but there isn't a negative. So Kelvin, so the lowest temperature that is possible is -273.15 Celsius. So in order to change that to a 0 degrees or 0 Kelvin, we would have to add 273. So this is where the formula comes from. So if we want Kelvin, we'll take the Celsius temperature and add 273. The reverse is true if we want Celsius. We'll take away 273 from the Kelvin temperature. Okay, and this is a little formula for converting between Fahrenheit and Celsius. One last thing that I want to mention is, because there's so many different conditions, we can use pressure, temperature. The International Society of Chemists have come up with two sets of standard conditions: standard temperature and pressure, okay, which is 0 degrees Celsius in 1 atmosphere. So that's kind of a fairly normal pressure. 0 degrees Celsius is okay too. The only issue is you're dealing with solutions. Some of those solutions are going to freeze at that point. So they've adjusted and taken into account a second set of standard conditions called SATP, standard ambient temperature and pressure. So ambient generally means environmental or surrounding temperature and pressure. So 25 degrees Celsius, 100 kilopascals. So 100 kilopascals is fairly close to the atmosphere, but the 25 now is more at a temperature that is normally used in experiments. I guess it would be considered scientific room temperature, even though 25 degrees Celsius is fairly warm still by our standards. Okay, so that's the main measurements we'll make for gases. Okay, with solutions, we introduce concentration. Now we've got pressure, temperature, and volume are all important. Okay, so we're just going to go through conversions, just do a few conversions here. Remind ourselves of the metric system there just a little bit, especially when it comes to volume. All right. Pressure, we're going to have to convert in between a bunch of different units that we're not necessarily familiar with. And then temperature, we're using a formula. Okay, so first we'll start with just reminding ourselves about conversions and how they work. They're all, with the exception of temperature, they're all conversions are made either by dividing or multiplying. So keep that in mind. Okay. So metric system, we have a base unit. So if it's volume, it would be liters. If it's a linear measurement, it'd be meters. If it is a mass, it'd be grams. Okay. So that's where our starting point is. Okay. So right near that base unit, there is a new unit that's fairly close. It's only off by 10. Okay. So a factor of 10. So, deci, okay, is a smaller unit by 10. So each time we go here, we're going to multiply by 10 because we need more of the deciliters or decimeters or decigrams than there were grams. Okay, so this is the way I kind of think of things. Down here at this end, we've got the small units. We need a lot of them. Way up here, we've got the larger units, okay? So we need less of them. So if we need more, we're going to have to multiply going in this direction. And then if we want less, we're going to have to divide. So go in the opposite direction. Okay, so that's a good way to kind of think of things. Okay, remember these are off by a factor of 10 units. And they're always multiplied. You're not adding these factors. So it's 10 times 10 times 10 to get to milliliters or millimeters or milligrams. Okay. Again, these are also off by 10, but you're dividing when you're going in this direction. Remember that. Okay. The next set of units, just for completion, they're not off by 10. They're all off by 1,000 from now on afterwards. So to get to the next unit, which is microliters or micrometers or micrograms, we're off by 1,000, and the rest continue that way. Kilos. Okay. Again, the next one is off by 1,000. That would be mega. Okay. So mega with a big M. Okay, off by 1,000, but we usually don't get into that either. Okay, so let's kind of apply this a little bit. So first things first, let's look at volume. Okay, so I have 8,759 liters, and I want to convert it into meters cubed. Okay, how do I do that? Well, a couple things I want to do is I am going from capacity to volume, so I do need to know the unit changes. So just earlier we realized that 1 meter cubed was 1,000 liters. So if I know that conversion, I usually line up the conversion just below it. And I try to see what happened. What do I have to do to this number to get that number so that I'll be a new unit at this point? And I realize I'm going from a large number to a small, so I am going to divide. I'm going to divide by 1,000 here. So if I do that with the units, I will also do that with the actual measurement I need. So I'm going to divide by 1,000. So 8.759 meters cubed. Okay, fairly straightforward. Okay, now I'm going to do a harder one here. Okay, so 24,730 millimeters cubed, and I want to turn it into centimeters cubed. Okay, now this is where we will get ourselves into trouble if we don't recognize that these are going to have different changes than the linear measurements. So I know that millimeters are smaller than centimeters, so there's got to be 10 millimeters to every 1 centimeter. So that's true for a linear system. But if I want volume, I need to cube everything. Now, the thing that happens that confuses people a little bit is that when I do that, I'm going to multiply 1 centimeter by 1 centimeter by 1 centimeter, and that number is not going to change because it's still 1. Okay? So it's going to be 1 centimeter by 1 centimeter by 1 centimeter, which, if I multiply the numbers, it's 1. Multiply the units, there's 3 of them, so it's centimeters cubed. So this doesn't change, but this does significantly, and it's not 10, because I am multiplying 10 millimeters by 10 millimeters by 10 millimeters. Multiply the tens together, it's 1,000, and the millimeters are all multiplied, so there's 3 millimeters, so it's cubed, okay? So the difference isn't a factor of 10 in volume, it's a factor of 1,000 for this 1 unit. Be careful with this. Okay, so as a result, if I line these up, 1,000 millimeters cubed goes to 1 centimeter cubed. Again, I'm going from 1,000 down to 1. I got to divide. I'm dividing by 1,000. I'll have to do that to this actual measurement, and it's going to end up being 24.73 centimeters cubed. Okay? So that's how you convert those ones. Why don't we at the same time, what is that in milliliters? Well, 1 milliliter equals 1 centimeter cubed, so that also matches 24.73 milliliters. Okay, just so you can see that conversion there too. Let's take a look at one last one for volume. Okay, so 25 meters cubed, and I want to go to centimeters cubed. Again, don't be fooled, it's not 100, because we're cubing the linear units. So if I kind of go to the side here and remind myself, well, 1 meter cubed is the same as 100 centimeters all cubed. This is now 1 meter cubed, and this is 100 cubed is 1,000,000. It's got 6 zeros, not 2 anymore. So I'm going from meters cubed to centimeters cubed. I am multiplying by 1,000,000 because they're getting larger here. Okay, so to get this, I got to multiply by 1,000,000. Okay, so it's going to be 25 million centimeters cubed, or 25 million milliliters. Okay, so that's volume. Those are a few different measurements, so there's some practice there in this handout. Okay, we're also going to look at pressure. Now this one's a lot harder because a lot of the units we're not familiar with. Okay, so let's just go through a few of these. So pressure. Okay, so say I want to go from 90 psi into atmospheres. Okay, so I know from the handout there before that 1 atmosphere is 14.7 psi. So again, if I line up, and I can do it below or I can do it to the side, 14.7 psi is 1 atmosphere. I can see that if I want to go from here to there, I'm going to have to make the number smaller, so I'm dividing by 14.7. That will give me 1, and in the same time, I will be changing the unit. So I can take the actual measurement and divide by 14.7, and that should give me my measurement in atmospheres. 6.12 is pretty good. Okay. Let's do another one. Let's go from millimeters of mercury to kilopascals. Now this is a little bit more challenging. Okay. So there's a couple ways you can do this. I am going to show you a straightforward way that you'll probably do intuitively. Okay. Then I'm going to show you a little bit harder way to calculate. I think it's good that you are introduced to it. So first step if I look at my conversions, they're all based on going from millimeters of mercury to atmospheres and then to something else. So why don't we do that? Why don't we start with step 1? We're going to go from millimeters of mercury to atmospheres. Okay, and I know that it's 760 to 1 atmosphere. I know that I will have to divide by 760 to get this. So if I do it with this problem, it's going to be 1,000 millimeters of mercury, and I'm going to divide by 760, and that's going to give me my value in atmospheres. So just over an atmosphere, looks like it. 1.316 atmospheres. Okay, so that's step 1. So I'm not quite there. I want to get to kilopascals. So step 2 would then be converting from atmospheres to kilopascals, which we have a conversion for too. Now this time we're going from 1 to this larger number, so I got to multiply by 101.325. So if I do that, take this atmosphere amount that I have, multiply by 101.325, I will now get my value in kilopascals, 133.3 kilopascals. And that's my answer. Okay? There is no real straightforward way to go directly there. This is probably the best, and these are the way that they're cited here. Okay, so now this is one system. This is using proportionality and kind of like a scale factor. Okay, another way that we can do this. Now, when you do these conversions, you really do need to show some work here, a little bit of work like this. Even if you know what you're doing, show a little bit of work just so I know I can follow you and see why you actually did that. And if it's correct, that's great. You're getting full marks. If it's incorrect, at least I can kind of see you get the right number. Maybe you multiply instead of divide. I can see where you're having some difficulties, maybe help you correct that, or at least give you part marks on the test. Okay. The other thing too is when you're done with these, with any number, you need units right beside it. These are actually the same thing. Okay. The fact that they have different numbers there is because they're in different units. So without the unit, I can't tell if this is correct or not. Okay. But a second method that I kind of thought is awesome. Now, first time you look at it, you may not be all that interested in using it. Okay. But at some point, you probably will adopt using it because it is superior than this. Okay. So the first thing that we may do is just take the unit or the measurement that we have and its proper units. Okay. Now I know I want to replace this with kilopascals. So what I may choose to do, okay, is I can use these conversions because they're equal to each other. I can use them in a fraction form, one on the top, one on the bottom, because they're the same thing, even though they look different. Essentially, any number over itself is equal to 1, like 2 over 2 is 1, 4 over 4 is 1. These technically are the exact same things because they have a unit attached to them. So if I were to write a fraction with 1 on the top and 1 on the bottom, I'm really creating a fraction that is equal to 1. So, and 1 multiplied by anything doesn't change the value. It may change the look of it, but it doesn't change the value. So where am I going with this? Well, the idea with this method is to remove units by putting them in the opposite spots. So if you had something in the top and in the bottom and you divided them, these are going to be, I'm going to lose these units. We used to call this canceling. These will cancel out because it's in the top of a fraction divided by the bottom of a fraction. They're gone. Okay. What that does is, as long as I put the numbers with it. So I got 760 millimeters of mercury, 1 atmosphere. What it does is it allows me to replace the millimeters of mercury with this new unit that's in the top in the same position that it was in. These ones are gone because one's on the top of the fraction, one's on the bottom, but this is now replacing it. So now I'm at atmospheres by doing that. And I could stop there and I would actually get this number. I would get my my value of 1.316 atmospheres. Because what this is telling me to do is, with any fraction, you multiply the tops together. So 1,000 times 1 doesn't change. Then fractions really mean divide. So divide by 760, which is what I did. But I'm just showing it a little different way. Now, the bonus of doing this is I can do it again really quickly and not have to write out a whole bunch of steps. I'll put another fraction here. And if I want to remove the atmospheres, I'll put it down here. The one I want to replace has to be in the spot that the atmospheres were before. So I want to replace it with kilopascals. And I can put those conversions, because I know that 1 atmosphere is 101.325 kilopascals. And again, the same idea, top and bottom, atmospheres in the top and bottom, they'll cancel each other out. And all that's left is that 1 unit for kilopascals. And again, what that tells me to do is to multiply. So whatever I got here, I divided, and I got 1.316. And then it tells me to multiply by 101.325, which is what I did. Okay? But it's just kind of showing all these conversions all at once in kind of a nice organized way. As long as you understand canceling. Okay? And fractions a bit. So let's see what this tells me to do. It tells me to take 1,000, multiply by all the numerators, so multiply by 1, multiply by 101.325, and then divide by all the denominators. And the only one that's really going to matter is the 760. Oops, better make sure I put the divide symbol in there. Okay, I should get the same answer as we ended with, and I do, 133.3. Okay, so that's another method. This is often used in physics. This is called the unit factor label method. Unit factor, because these are ones. Okay, it's not changing anything. These are factors there, okay, that we're multiplying by, and we're labeling the units in there. Okay, so that is another way to calculate it. Okay, worth playing around with that a little bit. Okay, last quantity we want to look at is temperature. Just going to do a couple. Okay, we're going to focus in on Kelvin to Celsius. Okay, we'll do one of each. All right, one little thing, it's a little minor point, but Kelvin is not a degree. Okay, so it's not degrees Kelvin, it's just called Kelvin, okay, for temperature. Whereas in Celsius, they are degrees. Okay, and same with Fahrenheit. So, 57 Celsius, how do I go to Kelvin? Well, I can replace it into this formula. Okay, so my Kelvin temperature would be 57 plus 273. Just add those. And like I said, this is the only time I'm adding when it comes to conversions, is these temperature measurements, because we want to adjust the scale a little bit. Okay, do another one. This time we're going to go from Kelvin to Celsius. So how do I go there? Okay, so Celsius is the Kelvin temperature minus 273. Again, subtract those, and I get the temperature in degrees Celsius, 144. All right, good luck with the practice.